We're fortunate today to have Professor Chung-Pei Ma from the University of Berkeley visiting us. She was a student, all your degrees are from MIT, before doing a postdoc at Caltech, brief stint as a professor on the faculty at the University of Pennsylvania, before taking her position on the faculty at the University of Berkeley in their astronomy department. She worked on a great many different topics. I wasn't sure what she was going to talk about today. She could talk about a wide range of things, from theoretical applications of cosmology all the way to, well, what she's going to talk about today, which is her work on supermassive black holes and local galaxies. She's one of the experts in the field, so we're very fortunate to have her. Welcome.
Okay, thank you, Casey. Should I use this?
Sorry, I forgot to make the presentation. On behalf of the physics department, we would like to present you with the laser pointer.
Thank you very much. And it's green. Is this on? Yeah, it's working. Okay, thank you very much for the invitation. I actually went to the last year of my high school in Houston, so I feel like I'm coming back home, and the Houston was Robert E. Lee High School. Okay, so I would like to discuss and summarize for you a recent observational program I undertook starting about 5 years ago. I'm primarily a theorist trained in cosmology, but about 4 to 5 years ago, we were doing a number of numerical simulations studying mergers of galaxies, in particular elliptical galaxies, to form even bigger elliptical galaxies. Some of the biggest galaxies in the universe are in the form of elliptical galaxies. I don't want to go into that theoretical calculation here, but in those simulations, however, we found some interesting hints for deviations in these structures of these giant elliptical galaxies at a very, very massive end. So that's when I started to look at the data, and then realizing that, wait a minute, actually a lot of the information hadn't been obtained, in particular about the central massive black hole sitting in these elliptical galaxies. Our simulation would indicate that the masses of these black holes and the properties of the galaxies would also look somewhat different from the lower mass ones. So that's how I got into the observational program. And I would like to summarize the results for you. It's an ongoing survey. But before doing so, I would like to highlight the contribution of my former graduate student, Nicholas McConnell. He finished last year and now is a postdoctoral fellow at the University of Hawaii. I know there are a number of graduate students here, and we all know that graduate students typically carry out the lion's share of a project, and he certainly did. And probably some of you know Carl Gephardt very well. He's on the faculty at UT Austin. So before describing our survey, I would like to just give you some motivation for why we would like to study or search for these massive black holes, and in particular, just more generally, evidence for astrophysical black holes that we know of. Okay? And now I'd like to describe some observational challenges. You think bigger black holes, bigger galaxies, they are typically easier to find, right? Easier to observe. So why had it been so long before we were able to do that? There's a couple of observational challenges that we were able to overcome. And then in just a little bit detail about how we do about the survey and how do we actually tease out the black hole mass. And then how the black hole masses are actually correlated with galaxy properties. Okay, but to start with, just very broadly speaking, there are two classes of astrophysical black holes that we believe exist. The first class is the type I will not talk about today, but there is the sort of more mundane, better understood type. And they are the end states of massive stars much more massive than our own sun. These stars, even though they have a lot of fuel to burn, they burn the fuel at a much faster rate, so they actually live very short time, and they're extravagant stars, and they die a spectacular death when the fuel is used up, and they will go through a supernova explosion at the very end state, and what's left behind will either be a neutron star or possibly a black hole. Okay, so these black holes we're talking about, these are remnants of 20, 30 to 100 solar mass main sequence stars. So what's left behind typically are in the order of, a lot of mass gets lost. So on the order of 10, 20, 30 solar masses. in contrast to the second class I'll talk about in a second, those we're talking about million to billion solar masses. So the best piece of evidence for this kind of astrophysical black hole is probably this X-ray source called Cygnus X1. This is, of course, an artist's rendition. Okay, the black hole is believed to be here. You can't see it, but this source has given us a lot of data because it's in a binary system. So there is still a main sequence star, its binary companion, that's still shining and giving out a lot of light. And then the mass is believed to be accreted onto the black hole in the form of an accretion disk. So during this process, there's a huge amount of gravitational energy that can be released, and the gas very close to the black hole can be accelerated to the X-ray emitting wavelengths. So this is a copious X-ray source, and people have a lot of optical data, not looking at this itself, but since this companion is wobbling, they can do a lot of measurements. So the current inferred mass for this black hole is about 15 solar masses. And there are a number of these. These are just binary star systems in our galaxy. There are many, many binary stars, and in fact, more stars live in binary systems than being isolated like our sun. And you require very massive stars to be producing this kind of X-ray binaries, but a number of systems are known within our galaxy. Okay, and people are gathering data, especially trying to measure the black hole masses. Today, however, I would like to focus on the second class of black holes. We call them supermassive black holes. Okay, and they are much less understood, but as people gather data in the past decade or two, they seem to be ubiquitous in the sense that in the nearby galaxies where we can actually look very close to the center, it seems like every galaxy may host a supermassive black hole at its center. Okay, at higher redshifts, I'll show you these quasars, active galaxies, are also believed to be powered by supermassive black holes. So that's the second class. Okay, they typically live at the centers of galaxies. How they came about is much less understood. For example, maybe primordially, early time, you have a ball of gas of 10 to the 5 solar masses. Maybe they could collapse in a single collapse to form a black hole, and then later on they accrete to form bigger ones. An alternative theory is maybe you can have a collection of the 100 solar mass black holes somehow, and then grow them to be bigger masses. So which scenario is correct, we don't know. There are a lot of theoretical studies of these models, but currently the data cannot constrain the initial Cs for these black holes. However, it doesn't prevent us from gathering more data on the properties of these black holes. So for the supermassive black holes, the best measured black hole is at the center of our own galaxy. Okay? And this is an infrared image of our own galaxy. As you know, we don't live at the center. We don't live at the center of anything. We don't live at the center of our galaxy. And obviously, people who teach cosmology, you always get the answer, do we live at the center of the universe? There is no center to the universe. And so this is, since we're off about, let's see, 25,000 light years, 8 kiloparsecs from the center of the galaxy, we can actually take a picture in the infrared, and you're seeing a lot of dust lanes, and there's a bulge of stars. Okay. Now, if we, of course, you can't tell whether there's a black hole based on this picture. Okay. However, in the infrared, people have been able to develop very sophisticated spectroscopy methods to try to zoom into the center. Okay, so the idea here is if you can get you can't see the black holes directly, but if you can measure the stellar motions of the stars orbiting very close to the black hole, you can probably infer something. So we have long suspected that there's something at the center, though, based on the radio emission, Sagittarius A star, and so on. There are various indications that there's something at the center which is very massive and that's gobbling up a lot of gas. But to infer its mass, however, require monitoring individual stars very close to the center and construct its orbits. Okay? And let me show you the movie by Andrea Geddes' group at UCLA, and another group that has been working on this is Reinhard Genzel's group at Max Planck in Germany. And this is actual images of the positions of number of stars towards the galactic center. This is 0.1 arc second. This is, on the order of several parsecs or so, and monitored over more than a decade of time. So as you can imagine, they need to pierce into this very dusty region. And infrared adaptive optics turn out to be the technique to do it. And they're able to trace, you can see this S2, I think, has almost completed an orbit by now. Okay, and I've done this movie so it runs backwards just for fun. You can see some of these trajectories. And remember, this is projected on the sky. Okay, so there's a third dimension you're not seeing. But they can use these, and they can resolve individual stars with amazing astrometry to know the exact position of these things. So you can see that they can construct the common solution, right, that's making all these stars go on these trajectories. And sure enough, the common solution is a very, very large mass of about 4 million solar masses confined within a very small region. Now, since they have monitored S2 to the paracentric distance, so that volume is so small that they can actually constrain basically, how much then basically they can constrain the tiny region that you need to pack in 4 million solar masses. Granted, there are people trying to say, maybe you cannot prove it's a singularity, okay, like a supermassive black hole. So people have said, could this be a collection of 4 million stars that just happen to be very, very compact? Okay, and the fact is, dynamically, it's impossible to keep them stable for that long time. And there are alternative, very interesting theoretical proposals that it's a boson star or it's a strange star at the center that have very strange properties, but you can pack it to this density. But interestingly, black hole, I think some of those cannot be ruled out yet, but they're so speculative that black holes are actually the most mundane explanation for this whatever mass is at the small volume that's making these stars orbit in such a fashion. Okay, so this is the best piece of evidence for a supermassive black hole, but this mass is actually puny. 4 million sounds really big, right? But I will be talking about things up to 10 billion solar masses today. However, to do measurements of other galaxies at their center, the nearest one, obviously, is M31, the Andromeda galaxy. It's at such a huge distance that it's impossible to resolve individual star orbits. Okay, so there you would need to do a statistical measurement of the stellar velocity distributions. It's sort of like a swarm of bees. When they're very close to you, you can kind of see these bees going around. But when you move that swarm of bees very far away, you will not be able to identify individual bees' orbits, but collectively, you can still measure their motion. Okay, so that's the technique we'll be using, still based on stellar kinematics, but not individually resolved stars, just because it's too difficult to do. Okay? But before turning on to these other galaxies, let me just show you some other places in the universe where we believe that supermassive black holes also are lurking. Some examples are these active galaxies. M87 is a giant elliptical galaxy in the Berkeley cluster. It has 10 to the whatever, probably 12, more than a trillion solar masses just in stars. And there's a dark matter halo surrounding it too. And it has energetic jets coming out. There are these radial lobes, and there are these various galaxies where at the center we see unusually active behavior. Again, indicating that there is gas, material, baryons being accelerated to very high energy and emitting these X-rays. So you need a very deep gravitational potential for that to happen. Another interesting example is, earlier on I talked about the binary stellar systems, and there are actually belief that we actually believe there are also binary supermassive black holes. Okay, and this may sound kind of weird, but it's actually not almost unavoidable. It's inevitable in the sense that, for example, the Milky Way has a 4 million solar mass black hole at the center. M31, we have a pretty good evidence for another black hole at its center. And we know that these two galaxies are on a collision course. The two spiral galaxies are going to merge eventually in how many billion years. And when they merge, we've seen this happening in the other parts of the universe. The galaxy will get scrambled, the stars will get scrambled, new stars will form from the gas being shocked, and the central two black holes probably will come together through a sync through dynamical friction to form a binary. That's actually a pretty dynamically favored state. So you can go out and ask, are there sort of double quasar, double active nuclei systems out there in the universe? And NGC 6240 is probably the best known example. Okay, and there's an optical Hubble image, but if you zoom into the center, there are two bright X-ray sources. Just a few kiloparsecs apart, I think. And each one is believed to be hosting AGN activities. They have all the signatures of AGN emission lines and so on. And the general belief is each one probably has a central black hole there. And of course, one big question is, would these two black holes eventually merge? Obviously, you need to lose a lot of angular momentum and orbital energy by kicking out stars. But if you could do that, then they could merge to form a bigger black hole. And the very final spiral of that process is believed to be the primary source of gravitational radiation. Not for LIGO, that frequency is too high, but for these space-based kind of interferometers. So supermassive black holes are very interesting sources of gravity waves. Yes, absolutely, they rotate. Okay, so these are just some evidence for active, we call galactic nuclei that's believed to be powered by supermassive black holes. I think another very important link to talking about our project, which is focused on the nearby giant elliptical galaxies, is the connection between these galaxies, like M87, is a very big quiescent galaxy, except for the jets. Is the connection between them and high redshift quasars. Okay? And I would like to sort of summarize the situation with quasars right now. So quasars are very active, luminous sources, kind of galaxies that appear like a star in the old days, okay, until you can get a redshift for these objects. And they're believed to be some of the most luminous galaxies where they host some of the most massive black holes at high redshift. High redshift is early universe. So this is a compilation based on the Sloan Digital Sky Survey of the quasars in their sample. And here you see the black hole mass plotted. Again, these black hole masses are not determined by these dynamical methods I just talked about, but rather they are determined using more indirect methods based on the width of emission lines. The belief is they're broadened by these motions, gravitational motions around the black holes. So they're not very precise measurements of black hole masses. However, the power of this kind of study is the statistics. There are thousands and thousands of points here, so you can at least get an overall census of roughly the black hole masses that's powering these quasars as a function of cosmic time. Okay. So this plot, what you see, generally speaking, is at high redshift, and this is when the universe was very young, much less than 1 giga-years old, there are some quasars whose central black holes have their suggestion that they're already reaching 10 billion solar masses. Okay, and you see this whole thing dropping. Of course, this doesn't mean that black hole masses decrease as functions of time. Okay, I know we're in the Hawking auditorium. Hawking radiation timescale is negligible for such a massive, supermassive black hole. So they can only stay the same or they accrete, they grow. They got to grow or stay the same. Okay, so this plot is not telling you that black hole masses are dropping, but rather in the quasar environment, okay, they host smaller and smaller black holes at lower and lower redshift. Okay, why this happens is by itself a story, but I don't want to get into that. Okay? But I want to highlight that. So this is telling us that these giant black holes existed at high redshift. Today, they are not living in quasars. Okay? But they should be around. That's the question mark I put here. So what environment should they live in? Okay? And the belief is, you look around nearby, probably the giant elliptical galaxies that no longer shine as a quasar. It requires a lot of gas and so on to power a quasar. So we believe that perhaps if we can do some measurements of the massive black holes in these nearby giant elliptical galaxies, maybe we can find some of these missing ones, establishing the link that would indirectly tell us that maybe high redshift quasars, they were going through a very active phase, but as they merge and use up the gas, eventually they become giant elliptical galaxies. So to link up this assembly history of quasars versus nearby massive galaxies, it is also a very interesting thing that we're trying to do by measuring finding these black holes. Where are they today? And another thing, just aside, I want to just emphasize without going into detail is black holes, although they live at the very center of these galaxies, huge amount of recent work on galaxy formation believe that their feedback on the surrounding gas can impact the property of the entire galaxy. Okay, in fact, in very many models, you really need these black holes to get rid of a lot of energy and to shut down star formation in order to create galaxies that look like what we observe today. To get the galaxy to be red enough, to shut down the stellar star formation rate, to lower the stellar masses in all these models, it requires the black hole to talk to the gas on a very large scale. Okay, so this feedback from black hole is right now a very active field of research in the understanding of galaxy formation. So that's another link in why one will want to understand these black holes, not just for themselves, but for their impact on the host galaxy. So the very last thing I'll show in the introduction here is that, and I'll show the real data in a second, is another physicists all love correlation. Okay? So among the nearby black hole masses that we can measure directly using stellar or gas kinematics, people have found that basically there's a general trend. This could be anything, stellar mass of the host galaxy, its velocity dispersion, or its luminosity. Basically, there's an overall positive correlation that is bigger black holes tended to live in bigger galaxies. Okay, so somehow the black hole knows about its big scale environment. Again, this ties into this feedback process. But this is just an empirically established correlation. I'll show you the first paper where this correlation was pointed out. And this was in 2 papers 13 years ago. And as you can see, there are 26 data points. And this is the black hole mass. Here, it's not based on emission lines. This is based on painfully constructed stellar orbits and so on. Okay. So there are we call direct mass measurements. And this is the velocity dispersion of the stars in the bulge, basically how deep the potential well is, how big the galaxy is. Okay, so in this paper, they point out that there's a positive correlation. I mean, no, this is 3 orders of magnitude in mass, and the slope is about 4. According to one, at the very, very center, right? So I'll show you more about how that's done. Yeah. And there's a debate about the slope. The slope depends on how the galaxy and black holes talk to each other. One paper said the slope is 4, the other paper says 5. Okay, so I will show you at the end of the talk our recent compilation of 72 such sources, and I think that gives us a better indication of what's going on. I just want to emphasize, in 2000, you can see the highest points are about 1 billion solar mass, 1 or 2 billion solar masses for the black holes. So the question is, are there things, right? There's no 10 to the 10th solar mass black holes as indicated in the high redshift quasars. So there's no reason to believe that they are not there. In fact, we would like to search for them. So another very interesting, I think, property of these giant black holes is the size of its event horizon. Okay, the Schwarzschild radius, and it scales linearly with the mass. So for 1 solar mass, the Schwarzschild radius is about 3 kilometers. So it scales linearly. So if you consider our report, our recent discoveries of 2 10 billion solar mass black holes, but just to give you an indication for the size of these black holes, of course it's a singularity, but the event horizon is about 5 times the size of the solar system. Right, so one question we get a lot is, should we worry about the black hole at the center of our galaxy? Are we going to get sucked in? Okay, the answer is don't get, for these huge black holes, don't get too close. But once you're outside of this, you don't care. Right? So let me then go on to describing a couple observational challenges for getting the very, very massive end of that scaling relation. And why were there no black holes found that's beyond 1 or 2 billion solar masses? So the first one is an obvious one, okay, that bigger black holes live in bigger galaxies. But bigger galaxies are rare. Okay, the mass function of a galaxy is a rapidly falling function. So there are a lot more small galaxies compared to big galaxies. So big galaxies are rare. Then you got to go to more distant places to find the next biggest galaxy. Okay. And the Virgo cluster, where the M87 giant galaxy lives, is only at about 17 megaparsecs. Okay. And their surveys of nearby elliptical galaxies are limited to only about 40 million parsecs. So you need to go beyond this. But then there's this issue, right? I just said earlier, you don't care about stars that are very far away from the black hole. They don't care about the black hole mass, right? Their orbits are dominated by stars and dark matter. So you got to go for the kinematics of stars very, very close to the black hole. Okay, and one measure of how close you have to get is called the sphere of influence. So this is another scale associated with the black hole in addition to the event horizon. Okay. This is a different scale, and that's basically G times M over sigma squared, just, Newtonian indication law, where when the mass of the black hole dominates, that'll give you the sort of rough radius of that size. Okay, so what you want to do is you want to measure orbits of stars within the sphere of influence in order to for the black hole to dominate the gravity there. So you put in some standard numbers where a galaxy velocity dispersion, very massive galaxies, about 300 kilometers per second. I'm just using 1 billion solar masses here as indicated. Then the sphere of influence is 50 parsecs, about 150 light years. Okay. That by itself doesn't sound like anything until you put this, as I said, you got to go beyond Virgo. So, let's take 100 megaparsecs as a sort of a typical distance to some of these very, very massive galaxies. They're all very well known. Then you put 50 parsecs at 100 megaparsecs, the angular size is 0.1 arcsecond. Okay, that's a very, very small, the full moon is, 30 arc minute inside the diameter, right? So this is 0.1 arcsecond that you need to resolve. Ground-based telescopes without adaptive optics, typical seeing you get in typical observatory is probably 1 arcsecond or 2 keck. The very best size may be 0.4, 0.5 arcseconds. Okay, so you need fantastic angular resolution in order to measure these stars very close to the black hole. Of course, when you have a 10 billion solar mass black hole, then this becomes 1 arcsecond. Okay, so that becomes a little bit more doable. So that's challenge number one, that distant massive galaxies are more distant, but you have to resolve your stellar kinematics to that small scale. Okay, so let me give you another analogy. Okay, so what I'm talking about here is, right, put it about 100 million megaparsecs. We're sitting here trying to pierce toward the very, very center of these galaxies to measure the kinematics. But the sort of sphere of influence for a 10 billion solar mass black hole is about, you can use something like 1,000 light years. That's sort of like sitting in San Francisco, looking towards Los Angeles and watching Yo-Yo Ma, say, performing cello, and you're trying to resolve how fast his fingers are moving. Okay, at that distance of that scale, it's just a rough scale. It's a pretty difficult thing to do. Okay, number one. So the second challenge is actually these massive elliptical galaxies have very low surface density stars near the center. Okay, this is just a surface profile, the sort of amount of light you see in stars as a function of radius from the center of each galaxy for a bunch of galaxies. Here, I just want to highlight that the solid ones are the more massive elliptical galaxies. As you can see, they tend to have this core profile. Okay, the density of stars started to flatten out near the center. The less luminous ellipticals, they actually have a higher density of stars near the center. And the center is where we want to get at. So to get enough signal to noise, okay, you need to collect more photons from these giant galaxies, ironically. Why this is true actually is by itself an interesting question, right? Why do they have a core? Seems like the stars have been kicked out. So one running theory is maybe you have the binary black hole I was talking about scouring out, kicking out stars near the center, and they can shrink further. Okay, maybe you can produce a core profile and so on. But this is an observational fact. So we need to, so what happened is the 20 or so data points I showed you, they were all mostly done with the HST, Hubble Space Telescope, because it could reach fantastic angular resolution. But it wasn't big enough, the mirror, to study some of the most massive ellipticals. So they smartly chose galaxies in the Virgo cluster. They're closer, and they have higher surface density, and they're easier to measure. Okay, so the combination of the two made these massive elliptical galaxies actually much harder to study. And about 4 or 5 years ago, we decided, well, one way to go is to use ground-based telescopes that are much bigger than the Hubble Space Telescope, the 8 to 10 meter class telescopes. So you have the collecting area to get enough photons. But also we can use adaptive optics, these new toys on the market that allows you to correct for the atmospheric seeing from the ground and achieving almost HST-like angular resolution. Okay, it's a combination of these new technologies that allow one to explore this parameter range. So let me just describe very quickly, briefly, show you just a little bit of data that we've gotten so far. Okay, so again, we're trying to measure something we can't see, and so we're using ground-based telescopes, and we also sometimes need adaptive optics, and we also use these. Clearly, we need spectra, right, to get the velocities. So we need spectrographs. And some of the biggest telescopes and smaller telescopes have these spectrographs called integral field spectrographs. Let me highlight the 4 we've used. In particular, the one on the right, some of you are very familiar with. This is a McDonald Observatory here, the Mitchell spectrograph. Okay. They cover different field of view on the sky, so we combine all of these for our studies. So the Mitchell spectrograph, these are all IFU spectrographs. So that means you have, for example, fibers. You can take one exposure, but you can get spectra from each fiber. So in one shot, you get spectral information on a 2-dimensional grid. This is a much faster and efficient way of getting spectra and studying galaxy dynamics compared to the traditional way of putting down a long slit. In the old days, people put a slit and disperse light in the other direction, so you only get information about, say, the major axis of a galaxy. Here, in one shot, you get what the stars are doing over a broad range of spatial coverage. And so the Mitchell is particularly good for getting a very wide field, so it allows us to study the stars on the outer part. They're not influenced by the black hole directly, but they also go into our modeling. Okay, but for the bigger telescopes, so this is the 2.7 meter telescope we use. We have used Gemini. This is an 8 meter telescope. There's a north and a south. This is a spectrograph, and another IFU that allows us to get this is still seeing limited. Okay, and then with adaptive optics that allow us to really zoom into the central point, 0.1-ish arc seconds, we use Keck-Osiris and Gemini's NIFs. Okay, so just to give you a flavor for each galaxy, we typically try to get data from multiple set of spectrographs just to get enough information about the stellar kinetics. Okay, so very quickly about one of the 2 10 billion solar mass black hole that we found, and this is the probably most famous cluster of galaxies beyond Virgo. Okay, and this is called the Coma Cluster, and here's an optical image. It's at about 300 million light years. And so all the fuzz here, most of them, they are elliptical galaxies residing in this giant cluster. Okay, we believe they're gravitationally bound. Now here you can see each one has trillions of stars, okay, and a much bigger dark matter envelope that you can't see directly. So you can see there are 2 very bright central galaxies, and the brightest one, the so-called brightest cluster galaxy, is NGC 4889. It's a giant galaxy, very high velocity dispersion at pretty far distance. So we tried really hard to get spectra of the very central region of this galaxy, for example. Okay. So here is a summary of where we are with our survey. Okay. So far we have published 5 black hole masses listed here. This is so 4089 is the BCG of Coma, and all 5 so far are the brightest cluster galaxy in a cluster. we're now enlarge our sample to include other massive but non-BCGs. And this is the distance, this is the velocity dispersion of the galaxy, this is the absolute magnitude. And I just want to highlight that the two red ones are sort of currently the record holder. They are reaching about 10 billion solar masses, which is very comparable to the highest redshift quasars with the highest black hole masses. Okay. And right now we have in hand data from those various spectrographs for 20 more massive galaxies we're analyzing. 5 are now being taken this semester, and we have proposal in for 8 more. So we are looking at a sample of 35 or some more galaxies to add to the measurements. Okay. So let me just show you a few spectra. Okay. That was an HST image. And here are, for example, from the Gemini, for 2 of these record holders, 2 galaxies. This is the central pixel of the IFU. We're using calcium triplet in the red to study the velocities. And Osiris spectrum is in the infrared because it's an AO system, and we use the CO band heads in the H band, and we're trying the K bands right now. These are just some sample spectra. This is from the Mitchell telescope. This is the outer part of the galaxy. This is the inner part of the sample galaxies. You see all these absorption lines. So the very basic idea here is, like what most people do, is when you have absorption lines, you convolve a template of stars with some kind of velocity distribution, right? For this ensemble of swarm of bees, they're presumably following some velocity dispersion, convolving with representative stars that will reproduce these line absorption features. You try to see what's the best fit of velocity profile to match your data. This is a pretty standard technique. So what we can get here basically is for each pixel or fiber on the sky, we can get a velocity, a full velocity distribution. Okay, not just the mean or the dispersion, but we can get the whole shape. So how do we use this kinematic information to construct black holes? Okay, that's our goal. So let me spend 2 minutes on that. So in addition, so that was the sort of the observational part of the project. Now, in order to use the velocity distributions we get from the IFUs, we actually have to perform a quite involved set of stellar modeling. Okay, again, it's not like our Galactic Center where you can nicely see the Keplerian orbits. Okay, it's all Newton's simple orbital construction. Here we actually have to do a Monte Carlo method called Schwarzschild orbit modeling. I'll very quickly walk you through the idea. It's very simple, okay, but it just requires a supercomputer time. It's a static problem. Okay, that's right. It's just computer time. So there are 2 parameters here, basically. One is the black hole mass that we're trying to determine. The other is actually the star's mass to light ratio. We measure light. We don't know the mass. We need a conversion. Okay. So this is just classical dynamics, a density where we postulate that black hole sits at the center. Okay. And then there are 3 components to the potential. One is at the very center is dominated by a delta function of black hole mass. And then there's the obvious stars that's sitting there. So this is the 3-dimensional deprojected stellar density that we can measure using the photometry. Okay? And we convert this light profile to mass using this mass to light ratio. That's the parameter number 2. And dark matter actually matters a little bit. I won't go into the details here, but we also put in a dark matter potential, and we add the 3 together. Okay? So everybody can do this, right? You have a potential. It's actually symmetric. And then you can just generate tens and thousands of allowed stellar orbits in a given potential. Okay? And you want so then it's a superposition of these. It's a Monte Carlo, right? So it's a superposition of these tens of thousands of allowed stellar orbits in the static potential. And you want the combination to reproduce the data. What are the data again? One is the observed light profile, right? I've shown you some of those. So we do need HST photometry for that. But the most important thing, obviously, that is you want your combination of your stars to reproduce the light, obviously. Okay? But the more important constraint is coming from that velocity distribution I spoke about, the line of sight. Remember, we can only measure line of sight motion. We can't get the proper motion. Okay? The line of sight velocity distribution I described just now. Those go into constraining these orbits. So for each combination of these two parameters, you can compute a chi-square, the best fitting set of orbits, and you repeat this over this two-dimensional parameter space to see which set of numbers give you the best fit. Okay, so a typical plot we will get for a given galaxy using multiple IFU data is something like this, that is a contour plot showing you the sort of most favored range of black hole masses, and along the way we get the mass to light ratio. Okay, so this is one of the record-breaking 10 billion solar mass black holes that we got, and this is the method we use. There are a number of model improvements which I will not go into right now, but I just name them. One is inclusion of dark matter halo actually changed the mass of black holes a little bit. I'll be happy to talk about it. But these are a few things to keep in mind. The shape of the gravitational potential. Okay? If it's completely triaxial, there's a very, very complicated code. There's one code that does that. And then the code we use is developed by Carl Gebhardt and others. It assumes axisymmetry about the major axes. Okay, so there are comparisons to see how they differ. And very recently, what we introduced was the model typically assumes a constant mass to light ratio conversion for a given galaxy. You saw that, right? It was 6 or something. But in fact, these giant elliptical galaxies all show some sort of gradient in color, in stellar population, and so on. So we're worried that maybe mass to light ratio could have a spatial gradient within each galaxy. We put this into the model to see how it could impact the black hole mass estimates. But so that summarizes the part about how we actually got the black hole mass for each of the sources I reported, and now you know the current state of the survey. So let me now just give you a few summary plots, okay, of the how these black hole masses are correlated with the galaxy properties. Okay, that has been sort of the holy grail of this whole field, is the fact that I showed you earlier that bigger galaxies host more massive black holes, indicating there is a very close relation in the growth of both. Okay, so how one impacts the other is a very important question for studying galaxy formation. So again, let me come back to this plot that first pointed out this correlation, at least the correlation between black hole mass and velocity dispersion of the galaxy. Okay. So recently, Nicholas and I, we compiled, things have changed a lot since 10 years ago. So this is our recent compilation, okay, of the black holes. They're mostly nearby, that have been measured using 3 different methods. So the way to read this plot is the different symbols refer to the 3 different ways of measuring black hole mass, all based on kinematics. Okay, so as I described, we use stellar velocities. So those are indicated as stars in the symbol. There are a few attempts of using gas around the very central region of these galaxies. Now, gas is a little bit more complicated because their velocities could be broadened by turbulence, by a lot of gas physics, while stars are mostly collisionless. Okay? So, but you can still try to use gas. And the third way, which I think is the most precise way, is to use masers. Okay? A very few sample, maybe 8 or so of these galaxies. Near the very center, there are amazing maser sources that people have observed. And these are so close to the black hole that they show Keplerian orbits. So it gives you a very, very precise measurement of the central black hole based on the masers. But they're far and few in between. Most galaxies just don't have masing activity near the center. But you can see those are the triangles here. There are basically the error bars on the black hole mass is so tiny you can't really see it. Okay. And the different colors indicate a different type of galaxies that the black holes live in. So the blue ones are the sort of late type, disky-like, Milky Way-like galaxy. In fact, Milky Way is sitting right here. It's a puny 4 million solar mass source here. And the red and the green refer to the early types, the elliptical galaxies. And we have highlighted the brightest cluster galaxy, these central galaxies, as green, just as a separate category. Okay, so I want to just point out that For a long time, M87 was the record holder. And our new points are adding to the top now. This is the Coma. Admittedly, with very large error, but 3842 was much simpler system. And so we have a website now compiling these 72 data points. So now we can do fits to see what the slopes we get. Okay. So again, I want to put the earlier Gephardt's plot on that just to show you the improvement. I mean, you can tell it's a pretty painstaking process. 13 years later, we have increased the sample by about a factor of 3. It's not an order of magnitude because each point is very, very time-consuming to get. Nonetheless, let me show you some of the fitting results. Okay, in the literature, the most naive thing, right? This is what 1, 2, 3. This is 4 orders of magnitude, right? So you see a bunch of points. Let's try a power law fit. Okay, so we did that to the entire sample. And as I mentioned earlier, there was debate over the past 13 years whether slope is 4 or 5. Now we're finding a much steeper slope. Okay, and two things contributing to that. One is, as you can see, our points tended to lie very high. Okay, so the overall global fit is indicated by the black dotted line here. So our points in the BCGs in particular tended to lie above the overall fit. The new maser points tended to lie below. Okay, so together they like to tilt the slope to a higher power law. And this epsilon refers to the intrinsic scatter in the relation. So we thought maybe now we have enough data points, it may make more sense to talk about these separate type of galaxies, to fit them separately. After all, early type elliptical galaxies are formed from a mechanism very different from that of spiral, disky galaxy like the Milky Way. So there's no reason the black holes are, should obey the same scaling law. So we have fit to the early types separately, the green and the red, and the late types separately. This is the first time I think there's enough data points to do this. And you can see that the error bars are pretty big, but the slopes have come down a little bit, still 5-ish. Okay, but the key here is one is the red curve, one is the blue curve, the fit. They're almost parallel, but the normalization are off by about a factor of 2. Meaning, for a galaxy with the same velocity dispersion, the early type galaxies tended to host a black hole that's twice as massive on average as the late types. Okay, so this is some sort of environmental dependence now. Why this is true, we don't know, and there are gazillion theoretical papers trying to reproduce this power law based on cosmological merger, gas accretion, and so on. And ironically, for the longest time, everybody, people can do these fancy hydrodynamical simulations. They merge galaxies. They make a lot of assumptions about how the central black holes grow. They say, we have no problem reproducing the Gephardt's exponent of 4. Okay, so now the question is, can they reproduce 5? I've done some of the simulations too. And I know there are plenty of uncertainties in the models that 5 is not going to be hard to produce either. Okay, so I think right now it's being very cynical about these simulations, but they're important to do, I think. I think pinning down the observational scaling law is quite important right now. Okay. So let me show you a couple other scaling relations. Okay, again, this is black hole mass, but this is for only early types here. You can look at the galaxy's luminosity. Okay, and this had been pointed out earlier too, that there's a positive correlation. The reason we don't plot late types is because it's hard to decompose the bulge from the disk. The belief is the bulge is the dominant, the spherical part is the important part. So people typically just throw out those points because it's very hard to determine the luminosity of the bulge alone. Okay. And this is our latest determination. And another very important scaling law is between the black hole mass. Again, this is the size of the galaxy. In this case, is the mass of stars in the bulge of the galaxy. Okay, and here you can see an almost linear relation. Okay, so bigger black holes live in galaxies with more massive bulges with almost linear relation and a scatter. Okay. So let me just spend 1 second before I wrap up about the scatter. Okay. So now these are the mean relations, and we've tried different fitting methods, and there are actually more sources with upper limits on the black hole masses. You can include them into the scaling law. We have a paper describing all the different things. I mean, there are small differences among the different methods, but overall, pretty consistent. Okay? So in addition to the slope for each of the relation, I think now it's time to talk about the intrinsic scatter about the slope. Okay? In this case, we can determine by adding the quadrature to the errors in the denominator, sort of standard way. So the way to think about intrinsic scatter is if you have very large error bars, then that typically one very small intrinsic scatter. If you have data points with very small error bars, obviously, quite spread apart, then the intrinsic scatter is very big. Okay? But we can quantify that, especially as a function of galaxy size. So I think this is an interesting new plot that we presented in our paper. Again, these are for different scaling relations. Let's focus on the lower right. Okay? So the plot here is the stellar mass of the bulge, like the last scaling relation I showed you. But on the y-axis now is the intrinsic scatter in the black hole mass in log mass. Okay? And there are different ways of estimating it. We tried. Let's look at the black squares here. Okay? So basically, you can see a scatter of about 0.3 to 0.4 dec. It's not small, and there's a not very clear sign that it's going to decrease, right? There are no error bars on here. We tried some Bayesian method. It's fairly consistent with that. I'll say almost flat intrinsic scatter. Now, why is this interesting? This is interesting because this provides independent information in addition to the scaling power law, the power law itself. Give you an example. There are a bunch of papers in the literature recently, theoretical papers, okay, that ask the question, I think it's a very interesting question to ask. Remember I talked about how these black holes were initially came about? We don't know. Okay? So they say, let's assume a bunch of galaxies with a spread of 3 decs in stellar masses at high redshift. Let's populate them with black hole masses that had nothing to do with the stellar mass. Okay, completely random stochastic distribution. So you can have very massive black hole galaxies hosting very small black holes initially. Okay, so let's just play this as a game. Okay. Then they feed into these semi-analytic galaxy merger models. So you build up the galaxies by merging and so on. But during each merger, they assume the black holes come together, they add up the mass. What they predicted was whatever initial, however, it doesn't really matter what shape this initial ensemble was, but it was just highly uncorrelated, it's just completely uncorrelated. What they found was through mergers, multiple mergers, as time went on, at redshift 0, they got a correlation. Okay, and the reason is due to the central limit theorem, really, that the outliers tend to be washed out as these blue points merge through generations of mergers. And their merger tree is actually fairly realistic based on numerical simulation galaxy formation models. Okay, but one big prediction of this model is as you merge to form bigger black holes in this theoretical model, the scatter decreases. Okay, in fact, they haven't even gotten to our range, right? Our math is up here. They almost predict 0 scatter. I guess everything got onto this nice relation. So they made big fuss about how you don't need the black holes to know anything about the galaxy. You start with random C's, you will get this naturally through central limit theorem. So now we will say that I don't think that they can get any slope they want, but I don't think the scatter is consistent. Basically, we observe too large a scatter to be consistent with these numbers. That's right. Yeah, I don't think they even bother with different morphology. That's right. Yeah, I'm not sure they worry. I mean, they added star formation to this model later on to see how they can spread this out a little bit. That's right. That's right. I think this case, I'm not even sure they considered this component. This is just an illustration of how the dependence of the scatter with galaxy properties by itself is a very useful information. And we think we can pretty much rule out these models. So let me summarize now so the previous compilation of black hole mass is not the 2000 Gephardt paper, but rather the 2009 Göttingen compilation that a lot of people use. Even compared to 2009, there have been a lot of updates recently. So we thought I myself was starting to get confused by which sample, which measurement was what. So we said, can we just put this on a website? And then we thought it would be nice to put this, maybe this public. And then it became the problem of what domain name we should use. So we tried, blackhole.net, blackhole.com, blackhole.whatever, and they were all taken. And they're not even being used, but people bought them all, thinking people like us will need them eventually. So you need to pay them some extraordinary amount of money to buy the domain and then pay them monthly fees or something. Right? I didn't want to get in, and I wasn't sure if we can use NSF grants for that. Right? I may get in trouble. So we thought, okay, that seems too complicated. So I was hoping to get blackhole.berkeley.edu. So I talked to our assistant manager who contacted the university. We have, what do you call, some master of the website. And they said it's being used, too. And it's being used as a mail server. I think they find it's funny to have, Blackhole, the mail server. That sounds about right, especially for UC Berkeley email service. But fortunately, they were very gracious. They immediately recognized that we're in the astronomy department and that black hole probably has more meaning to us than to them. So they gave it out immediately to us. They just had to point the website to another thing. So we've grabbed this, and then we just try to update this when new measurements come in. Okay, and again, what has allowed us to probe this higher mass range is because of the instrumentation, the combination of ground-based telescopes, the big telescopes, with the IFUs, the 2D spectra we can get, and adaptive optics with the resolution. And so now we're able to push the measurements beyond the local 2040 megaparsec to about 150 megaparsec. Of course, GMT or TMT will be great for this future project. Okay, and we have found some brightest cluster galaxies, some of the most massive galaxies in the universe. They seem to host black holes up to the order of 10 billion solar masses. So at least those two question marks I put there. Now it's looking like we're starting to find some of the local counterparts of the high redshift quasars. And as I show you, we are busily analyzing the data right now. We don't know, not every galaxy will give us a robust black hole measurements because the kinematics may be too complicated or so on, but we're still hopeful we can get quite a few measurements out of this sample, and we're still getting more data. Okay, and for the scaling relation, that's the sort of the exciting part that have been used a lot in this field, and we would like to advocate that now when you have enough data points, 72 is not a whole lot, but it's better than 20. I think a global fit may be just a little too naive. Just because when you build models for galaxies, you always talk about early type and late type separately. Okay, so we think now we can look at separate behavior and you can see the offsets and the slopes and so on. And the last thing I didn't quite mention, but here is this M sigma relation, which has been the most exciting relation, is this sigma, this velocity dispersion of the entire bulge. Now we have a two-dimensional spectrograph to measure sigma. So every galaxy, we actually can measure the profile of the velocity dispersion in function of positions. So now it's becoming not clear which sigma you actually want to plot on the M sigma relation. Okay, for those of you who do stellar galaxy dispersions, you know that. So the question may be which sigma will give you the tightest relation as a good proxy for the black hole mass. So in modelers, the thousands of papers I've mentioned, 999 probably paid attention to how M black hole grew, and then sigma, they just didn't do much about it. I think it's important to pay attention to both the galaxy and the black hole mass. Okay, and as I mentioned, the scattering the relation now is starting to rule out some of the models. Right, so what we're sensitive to is not a precise profile, but rather the total enclosed mass. Okay, and And you're absolutely right that if you can actually get the stars very, very close to the black hole, then you shouldn't worry about the dark matter at all. For our galactic center, no one worries about the dark matter because dark matter is way too diffuse to matter on that tiny scale. But for these other more distant galaxies, almost every other galaxy, all the other galaxies people have looked at, the problem right now is we kind of resolve the sphere of influence somewhat, but not superbly, just because of the limitation of the instrumentation. So then at the inner part, the orbits are sensitive to black hole and stellar mass, as you saw. The stars are more concentrated compared to dark matter. So to break that degeneracy, that's why we use the Mitchell telescope for the outer part, where that kinematics probe not black hole there, but stars plus dark matter. So we use the outer kinematics to constrain dark matter versus stars, and then trying to break the degeneracy toward the center. So what people found recently was when you include dark matter halo in the modeling, on the outer part, since it's a sum of the two terms that matter, and we know dark matter is there. We don't know its precise distribution, but it doesn't quite matter. It's a total amount that matters. Then you allow for dark matter halo, then it lowers the amount of stars you need on the outer part. Then, which translates toward the center that you need a higher black hole mass. Okay, and that's how the M87's number black hole mass had increased by a factor of 2 in the past. Right, so in the modeling, it doesn't care, right? It generates whatever allowed amount of, it allows for any kind of anisotropy in there. So it's, but you're absolutely right. So we can look at the best fit model and look at the orbital anisotropies that the model preferred. And invariably what we found was, first of all, the chi-square prefers a black hole, okay? And indeed, we see tangentially biased orbits toward the center, and the outer part is more isotropic. And I think that accounts for the, because we only measure the line of sight velocity dispersion, right? So we have that degeneracy. But the model clearly favors that, and indirectly that's consistent with the scouring idea that when you have, say, previous generation of two black holes merging, they like to kick out stars on low angular momentum orbits, right? Very radial orbits. Those stars get slingshot to the outer part. So that could remove that radial, those orbit stars with radial orbits, giving you a tangential preference. It is, yeah, I don't think we plotted this here. It's above the limit, I think. Yeah. So I think that's one interesting thing so far is there are about 90 other black hole measurements I didn't mention. Those are all upper limits. The interesting thing is the upper limits are all above the scaling relation. So there hadn't been, so put another way, there hadn't been a galaxy where you can actually say with very high significance that it has no black holes below, it doesn't fall below the scaling. Well, I think omega Sen is the one famous example, right? The intermediate and G1. Right. It's still not very clear, right? Well, do you know where the center is of LMC? Yeah. But there is no. Yeah. Yeah. That's right. Yeah. Right. I think he's referring to you. Yeah, maybe we should talk after. Yeah. Three. That is a very good question. So the answer is yes, but only for very few of the data points because like the most famous one, Maser 4250A, that had been measuring the stellar kinematics, and that is consistent with the Maser measurements. However, for M87, there have been earlier measurements based on gas, and that number is about a factor of 2 lower than the stellar method. Okay, so not every galaxy had these tracers. So it's only in the rare cases where you can use 2 of the methods to compare them. But I think it's a very important comparison. Thank you.